Okay, YouTube, this is my first video in which we're going to be exploring rational expressions, most notably how to simplify them, restrict their domains, or write the restricted domains, add, subtract, multiply, and divide them. Okay, so let's go ahead and start in this video. We're going to be discussing basically what they are and how to simplify them, as well as how to multiply and divide them. So a rational expression, I think it's worth noting here that the root of the word rational is ratio. So these are essentially ratios of polynomials. Okay, so if you had a polynomial divided by a polynomial, you have a rational expression. So we say the quotient of two polynomials is a rational expression. Also, the set of real numbers for which an algebraic expression is defined, we refer to that as the domain of the expression. So basically all the values of x for which when we plug them in we get a y value back, or at least a value back, and is not undefined. Because rational expressions indicate division, and division by zero is undefined, it says we must exclude numbers from the rational expressions domain that make the denominator zero. So basically, when we look at rational expressions such as the ones you see listed here, we're always constantly in search for any x values that might cause us to get an undefined value when we plug that in. So what we want to start with is this. We want to be able to find the domain of a function, or at least restrict the domain if it is restricted, find what those restricted values are. So the method for doing this essentially is when you have a rational expression, if we want to find the x values that would cause it to be zero, what we do is we take the denominator and we actually set it equal to zero. So in this instance here, if I said, well, what would cause this to be true? We could just go ahead and solve this equation. If we subtracted 5 from both sides, we can see easily that -5 is not in the domain of this function right here. So we would say that the domain, we'll write this in set builder notation here. We'd say the domain is all x values such that x is not allowed to be -5. That's how we would write the domain of this function right here. Taking a look at letter B, I'm going to kind of stretch this out here. We notice I've got x over a difference of squares here. So in order to solve this here, we say x squared minus 36. To find its restricted domain, remember we're going to take the denominator and equate it to 0. So there are two ways we can go about this. One way is to actually just add the 36 to this side. And we get x squared equals 36. And when we take the square root of this, we actually get two values. We get plus 6 and minus 6. So there are two restricted values here. And the other way to solve this was to kind of just factor. We say x minus 6, x plus 6 is equal to 0. And if these two things multiply out to be 0, then either x minus 6 is 0 or x plus 6 is 0. And it's easy to see that we arrive at the same conclusions here. X equaling 6 would be 0 here, or x equaling -6 would be 0. So this one's domain, we would say, is the set of all x values such that x is not allowed to be equal to plus or -6. So now we say this last one here, 7x over this trinomial here. And I notice that this trinomial here is factorable, but again, what we're trying to do is say, are there any x values for which the denominator is equal to 0? So we'll set this equal to 0. That's our method. We're going to set the denominator equal to 0 and solve it. So now this one we can't solve by any method but factoring here, or at least that is the most convenient method. I don't want to restrict any other methods here, but I notice that if it's a trinomial, we'll start with x and x here to give us our x squared. We say, what are two factors of -14? Well, one's got to be positive and the other one's got to be negative. And, it's worth noting also that these two factors have to add up to be -5 here in the middle. So I would say that it's probably a -7 and a +2. And we could check this by checking our outer and inner. We notice we get -7x and +2x adds up to -5x. So if these are factors, we have a factored expression set equal to 0. We can set each individual factor equal to 0 and solve those. And it's pretty clear that in this first instance here we get x is -2. In the second instance here we get x is +7. So that being said, we would say listing the domain of this, we'd say the domain of this function here would be all x values such that x is not allowed to be equal to -2, nor is it equal to 7. Everything else is acceptable. Okay, so let's talk about how we simplify rational expressions. When we talk about simplifying a rational expression, we basically say that the numerator and denominator have no common factors other than 1 or -1. It's just the same reasoning we would use here if I said that I had this expression here. I would not want to leave these b's intact because I know that I could divide those out of the top and the bottom. So using that same reasoning, when you simplify a rational expression, here are the steps we'll take. We're going to factor the numerator and denominator completely and divide out, any common factors amongst the two. So the reason why we factor is because, look, we've got a sum over a sum. And what do we know about writing things in factored form? Well, what you're doing is rewriting it as a product. And so we can cancel out common factors in those products. So looking at the top, I noticed that they have a common factor. I almost said common denominator. A common factor of x squared. So it'd be x squared times x plus 3. And in the basement here, we have x plus 3 as our factor down here. So the simplified form of this expression here would really just be x squared, or x squared over 1. Whereas when we look at this example here on the right, we have a difference of squares on top. So when I factor it, we factor into conjugate pairs. And then in the basement here, this is kind of, it's a sum, or it's a perfect square trinomial, but we can see we have squares on the outside, and I noticed that the middle term is 2 times the x times 1, which are the square roots of those. If we didn't know that, we could just do our trinomial guess and check. I've got x and x gives me the x squared, and then I would say factors of 1, of which there aren't many, we say 1 and 1. But basically what I notice is that these two factors cancel out. I'm left with x minus 1 over x plus 1, which those aren't common factors with one another. So this would be the simplified form of this. So while we're on the topic of simplification and that sort of thing, let's go ahead and take a look at multiplying rational expressions as well as dividing rational expressions, because they kind of operate on the same note. So it says the product of two rational expressions is the product of their numerators divided by the product of their denominators. In other words, you multiply fractions straight across. I'll tell you though, instead of actually multiplying these straight across right now, we're going to have a lot of multiplication to do and a lot of simplification to do. What we're going to do is we're actually going to factor all the numerators and denominators completely, because what we want to do is simplify it at first. So you notice I say divide numerators and denominators by common factors. That's the exact same thing we just did on the other page, except for we want to get those common factors out before we multiply. To give you a solid numerical example, this would be the same thing as me saying, something to this effect. And if I were to multiply this now, I certainly get 20/6. But I want you to notice this. This can be simplified, whereas if I had taken out any common factors to begin with, any of them, all of them, then I would have been left with 4/3, which I guarantee you would be already in simplified form. So what we want to do is simplify first. And so we have this expression here. We have x plus 3 over x squared minus 4. Now I notice that's a difference of squares. We're going to factor it into conjugate pairs here. We're multiplying this now by these. Now I've got trinomials, so we're hoping to factor these into products of binomials. It's possible that they're prime, but we say this one here would have to have an x and an x for the x squared. And then two factors of -6 that add up to be -1. I'd say have to be a -3 and a +2. Okay, and we can check that your outer and your inner, you would get a -x as this middle term. And then in the bottom here, that's a perfect square trinomial, but let's say I want to guess and check. Well, I've got x times x is x squared. Factors of 9 that add up to be 6 here, we'd say a +3 and a +3. So notice what's going to happen here is we are able to drop out this x plus 3 here and this x plus 3 here. And it's important to note also that this is a 1 up here now if I've divided that out. But also that the x's plus 2 drop out, and those are our only common factors there from the numerator to the denominator. So our final product is actually x minus 3. And then on the bottom we had this x minus 2 multiplying straight across. We would get x minus 2 times x plus 3. And this would be our product here. Now it is natural to actually carry out the FOIL in the basement here, but I'm going to say that that is acceptable at this point. Okay. So looking at a quotient of two rational expressions, basically what we're going to do is rewrite this as a product using what we know to be true, which is when you divide with fractions, we're actually doing an equivalent thing as would be multiplying by the reciprocal. So we can say 3x squared plus 3. Over here we get x squared plus x minus 2. And you notice that all I've done is just rewritten it as a product. So really, essentially, we're doing the same thing. So let us take a look at this here. We say that this top expression is a trinomial. We could look at that as being the same thing as having an x here and an x here. But the product of these two binomials, we say two numbers that multiply to be a +1 that have to be a -2 would have to be -1 and -1. Looking at the basement down here, the denominator, I notice they have a common factor of x. So I'm left with x squared plus 1. I do want to comment on this. I can't factor that because it's not a difference of squares. So that's going to stay where it's at. Now looking up here, I notice that these have no greatest common factor. So this stays as 3x squared plus 3. And then down here, we'll try to factor this into the product of two binomials, starting with x and x. Two factors of -2 that add up to be a +1. Would be a +2 and a -1. So looking for common factors now, I notice that those drop out, okay? And what we're really left with is this product here. So I'd say on top, multiplying straight across, I would get x minus 1 times 3x squared plus 3. And this is all over now. In the basement here, we've got x squared plus 1 and x plus 2. where I know I can't reduce any more of this because I got rid of all common factors up here. So again, you may be asked to go ahead and multiply this back out again, but since we took the time to factor it, I say let's just leave it there as our quotient. Cheers.